a great pleasure to be here. It's a bit of a last-minute thing that I was inserted in this program. So I'm only doing one lecture, but it's a great honor to do one lecture. It's also a little bit intimidating because you guys are all so smart, and I'm sure you're going to ask pretty nasty questions. So, which you should do, by the way. No reason not to do it. I'm going to talk about these two topics. I'm basically from the last generation, which is graphical models, which I really like, and I'm sure you've heard about causal models, which are also sort of in this domain. But you know, I also recognize that deep learning is kind of interesting. It's definitely making a big impact, and I've sort of tried to make a business out of combining these two a little bit. And this is also the story of today. So here's a bit of an overview. I'll say a few words you probably all know. I'm just saying them anyway, just to give my perspective on machine learning. I'll say a bit about graphical models. Maybe you've already seen this, so I'm not very, I actually don't know what you have seen and what you will be doing. So I'm just, it's a few slides. Then I'm going to talk a little bit about inference, variational inference and MCMC. Then I'm going to move to learning, expectation maximization, amortized EM or amortized inference, variational autoencoder. Then I'm going to sort of muse a little bit about discriminative versus generative modeling and why both of them are important. I'll say a few words about deep learning, about CNNs, and about dropouts. And that's I'll end with basically giving a Bayesian perspective on deep learning and some of the work we've been doing in MLab as well, and Bayesianizing sort of. And then I'll end with a really cool application to compression, actually. So people know Bayes about, you know, it's good because it will give you uncertainty over your predictions. You can do model selection. You can do all these nice things. But in fact, the coolest application, I think, is actually in compression. It's a really, I think, success story where we could massively compress neural networks by something factor of 400 without any loss of accuracy. Okay, so this is the main actor of today, and so you'll see that this particular equation will come back again and again and again in different forms and shapes with different variables inserted for a V. And so my main goal is that after this tutorial, this equation is your friend, and you completely understand it, and you'll be ready to apply it to sort of all sorts of applications yourself. And it's interesting, there is a sort of physics analogy to this where, you know, this is, including actually one of these terms is like an energy term, and so that there's an entropy term hidden in here in this KL. So there's a energy minus entropy, which is actually a very fundamental equation in physics as well. But also in compression theory, you can think of this as error of your sort of predictions, the remaining error of your predictions. And this is sort of a complexity penalty, which you know, penalizes overly complex models. And so there's many interpretations of this, and I feel this is a very fundamental equation to make your own. So one thing I want to say is that, you know, in deep learning, and maybe here it's not very necessary to say this, but in deep learning, many people are starting to view deep learning as basically an optimization problem. It's basically they say, you know, I have some data points, and then, you know, I have an objective, and then I have a huge number of parameters, and then I really need to sort of, you know, just optimize the hell out of it for a week on GPUs in order to get the best possible performance. You see a lot of you know, engineering going into, you know, doing this optimization right. I'm not saying it's unimportant. It's actually very important because you often see that even after a week of optimizing on ImageNet, you know, even the test curve error is still going down. It's interesting. But I also want to emphasize that, you know, deep learning as a part of machine learning is actually also statistics. And there's things about statistics that you just can't get out of an optimization view. And the first, you know, example that I want to give is, so let's say that you have trained, so under one of these objectives, so here's just a bunch of objectives. This is an unsupervised objective, the probability of your data points, you know, on a parameterized model, you're trying to maximize all parameters. For supervised, you often look at, y given x, and often these things sort of nicely sort of factorized because you can assume IID samples. Or you look at the minimization of some loss, where this is your prediction for a data point xi under some model. This could be a neural net. And then you sort of compare the prediction to the observed label and then minimize that loss. That's things. But now let's say that you drew one sample out of your distribution P. Right, so this is just one random sample that you drew, and you do optimization until you can't optimize anymore. So the whole thing is just completely nailed, right? So then you get some estimate for your parameters, theta MLE, that's a maximum likelihood estimate, which depends on your data. Now, a completely valid thing to do is to redraw another sample. After all, you just saw one sample out of infinitely many that you could have seen. So the next one that I draw from P is equally good, but there's nothing worse or better about that sample. And I could do another optimization all the way down to I can't optimize anymore. But then due to stochasticity in these samples, these two estimates are not the same. And in fact, they sort of, they might actually differ. Let's say this is the space of parameters. One is here, the other one is there, third one is here. So they form a distribution over parameter estimates. And now you can argue that your optimization should really not be any more accurate than sort of this region, right? Because if you go, more deeper, you're trying to figure out more detail, then really it doesn't make sense because the estimates themselves fluctuate if you redraw the samples. Now that kind of argument, about how to avoid overfitting and thinking about generalization, I think you can only get from thinking about this as a statistics problem and not just as an optimization problem. So for me, this is the most fundamental sort of thing in machine learning, which is thinking about the Biasvariance decomposition. Maybe you've already seen it in one of your lectures. Maybe you will see it again. I think it doesn't hurt to look at it a few times. So the way I view this is, so you have complex models and you have simple models, right? So let's say you're trying to, you build a machine that is throwing darts, at a target, right? And now if you have a really simple machine, like some spring or something that shoots things, then, you could imagine that when it shoots, it always shoots at the same position. There's not much variability, right? And it could shoot right in the center, but it could also shoot sort of off the center, right? So this would be a systematic error. Now, if you have a very complex model, let's say a very complicated machine, and I don't know, it vibrates or it has certain properties, then all these darts will sort of scatter much more broadly. So that corresponds to a much more sort of complex model, right? And then so this we call a model. So you can think of this as if you really want to do regression on a curve and you have a linear model, but it's too simple. You just can't get to this point. You just have to be off a little bit. But you have low variance. You always get the same linear curve, even if you have not so many data points. If you have a much more complicated model, every time you redraw your data, you'll have a different solution, right? And basically, of course, we want to be here. We want to have the right model, and we want the model to be as simple as possible. But usually, we are more like here, or even like here, we suffer from both things. So in equations, you can think of sort of the label y is generated by some true function f of x plus some noise. And the noise basically is drawn from some normal distribution. So we're basically after trying to figure out what that f is, right? And we have an estimator f hat, and we're interested in the error that we get between y, which is the labels we observe, and f hat. And so we look at the expected squared difference between these two. Now, using some math, you can decompose that into the following terms. The first term is the expected value over your estimator, let's say over many times redrawing the data set, right? That's this thing. f of x is the sort of the truth, right? And so this is how far you're off. So this is on average, how far you're off. That's the bias. The variance is only looking at the estimator itself and computes properties of the estimator, right? And this is saying what is the variance of the estimator. So this is like what's the spread function. And then there is this additional sort of noise term which you can't get rid of, which is basically how noisy your observations will be. Right? So the error can be decomposed in bias squared plus variance, irreducible error. And then, what's important if you sort of move in this model complexity space, so on the case where you have really simple models, your error is dominated by bias, right? Linear regression function doesn't fit to a curve that's not linear. Here's your error is dominated by bias. On the other hand of the spectrum where the complexity is really high, your error is dominated by variance, right? And and since you add these things up, somewhere in the middle is the optimum. If you're here, you're overfitting a lot. If you're here, you're underfitting a lot. And somewhere in the middle is where you need to be. So that's, I think, a super fundamental thing to always keep in mind when you do machine. We're going to tell a few things about graphical models. Again, you might have seen all these things, but I'll just introduce them briefly. It's basically a very concise and beautiful representation to read out conditional independencies between random variables. And the important thing here is that the random variables all mean something. So, we write down, and if you talk to an economist or something like that, they actually, when they model things, they mean that they write down variables that mean something to them, and then they try to figure out what the relationships between all these variables is. It's not like machine learning where you have a black box that we train on a huge amount of data. So, here's a particular graphical model, right? So we're modeling traffic jam. Let's say traffic jams, and there's a bunch of variables that influence it. So rush hour influences it. Bad weather influences the traffic jam, but it also influences accidents, which then again influence traffic jams, and then sirens are also influenced by accidents. We can write down the joint probability distribution over all of these variables as, basically you take the probability of a particular variable given all of its parents. Probability traffic jam given rush hour, bad weather, accident, times the probability of sirens given accident, times the probability of accident given bad weather, and then times the probability of rush hour and probability of bad weather. And the beauty is that if you want to read out some conditional independence relationship here, you can basically read it out. You can say, this is independent of this, marginally. Just read it out, and I'll show in a minute how you do that. And you can do calculations here by actually marginalizing out all these other variables. And then you get something like the joint probability between rush hour and bad weather factorizes into probability of rush hour times probability of bad weather. Right? And one other one, is rush hour independent of bad weather given traffic jam? Right? No, because there's an explaining away phenomenon that if you observe traffic jam, and bad weather is explaining traffic jam, then I don't have to explain it anymore by rush hour. You can actually move this probability. Now we can. And there's this beautiful algorithm called the baseball algorithm that will actually. Oh, you didn't know this? So there's an algorithm which beautifully and also mechanistically can figure out for you whether variables are or are not conditionally or marginally independent. So we can try to figure out whether this variable and this variable are independent marginally, right? We can check it with the equations, but we can also try to run this algorithm. Now this algorithm says if they're independent, then there should be no path from one to the other that gets that is not blocked, right? So you should not be able to get from rush hour to bad weather by basically bouncing a ball in this algorithm around using these rules, right? So now we are not conditioning on anything, which means we are not observing anything. We should these rules here, because this filled means you condition on it. And so, in going from here to here, I will have to go through sort of this thing, or I have to go through this thing, or I have to go through sort of this path. There's all these paths that I can take. But anyway, I have to sort of go through a path where two arrows point on the ball, and that's this rule, and it says it's blocked. If it's not observed, it's blocked, meaning there's no way I can get from rush hour to bad weather, meaning they're independent. Now, if I condition on traffic jam here, I'll have to use this rule, and now you see its free path is freed up, which is explaining away. Now you can move from here to here, which means that they're dependent. Information is flowing in this graph between these two nodes, and this means they're not dependent. Now, there's another collection of graphical models which is really useful, which are called Markov random fields. Now, there is no edges on the links, which makes the whole thing a bit simpler, because now you just have to say two variables are independent if every path between them is blocked. But the rule is now a lot simpler because you don't have to worry about all this set of rules. You just have to see, can I actually get over the graph from here to here? And I get blocked by observed nodes. So so these nodes are independent of these nodes given these nodes. It's a very simple rule to read out the independence relationships. And again, you can also write down a probability distribution that matches these conditional independence relationships by writing it as a product of maximal cliques, where a clique is the largest connected subgraph. So this is a clique, maximal clique, this is maximal clique, this is one, this is one, this is one. But you define potentials, functions on these collections of variables, positive functions, that's important, if positive. You take the product and then you have to normalize, and this is typically the nasty object because you can't even compute it most of the time, and so you have to approximate it. And so for learning, that's actually quite difficult. Right? So again, the Hammersley-Clifford theorem now says that if all these functions are positive, strictly positive, then the additional independence relationships between the graph and the probability distribution. Now, the next thing I want to do is introduce latent. So the previous thing, I didn't really sort of make the distinction between observed variables and latent variables. But when you model, let's say, some objects like these, for instance, the pixels in an image, then you can write down a model directly on these variables, right? But if this is a very complicated model, it's not so hard to hook up a sort of complicated model here. So easy. And so one way to do that is to imagine that these variables are actually caused, in the sense of maybe even previous lecture, by some other, latent variables, confounders, if you want, right? So we don't know what these are at this point. They could be known things, but they could also be unknown things, like topics in a document. Don't necessarily know already what the topics are, but we're just going to learn them. So there are the fundamental degrees of freedom, if you want, that influence the things here. And things like factor analysis are sort of a simple example, simple linear Gaussian example of sort of a model like that. And the object of interest is the probability over the data X. And now the reason that this can become complicated is because you can now write it as P of X given Z, X given Z. It's just a Bayesian model, I just discussed before, times the P of Z. Right? This is the natural decomposition for BaseNet. And then you have to marginalize out everything that's unobserved. And now this thing can actually become very complicated. So this is actually a very expressive model. If you don't choose everything linear and Gaussian, then it's a model. However, there's always a problem, of course, when you write down complicated things. And the problem here is that for learning or for doing inferences, you need this probability of Z given X, which is the sort of posterior distribution of your unobserved nodes given your observed nodes. And that, again, is non-trivial. So there's two ways to handle this. Well, there's more ways, I'm sure, but so there's two main streams of algorithms that are sort of complementary to handle this problem, the inference problem, computing P of Z given X. And the first one is variational inference, where you basically say, well, this is my probability, let's say the posterior that I'm interested in, but it's too complicated, so I'm going to restrict myself to a family of simple distributions, maybe Gaussians or The bigger set, nowadays we can make this set pretty big. And then we just find the best member of that family that's closest to the distribution of interest in some sense, and this sense is actually like minimizing a KL distribution. And it's nice because it's deterministic, right? This is just an optimization problem for this problem. It's biased, which means that you never can get to P. So even if you have like an infinite amount of data, or if you were doing a Bayesian problem, then you never ever get to P. So there is a gap always, and so that's a bias. The optimization problem itself is difficult because there's many local minima, but the nice thing is it's easy to assess convergence. Now the alternative is complementary, which is to represent the distribution of interest as a bunch of samples. So basically we're going to say that this is a complicated distribution, but we're going to draw representative samples proportional to the probability itself, and they are randomly drawn. Every time you draw them, they're a bit different, which means that we now have a different type of error. We now have stochasticity, which means that we have variance, sometimes called sampling error, right? So for any particular sample that we draw, right, we have some error because it's off, right? And for the next sample we draw, it's a little bit different. Now, it's an unbiased estimator, which means that if I do this infinitely often and I take the average, then I'm correct. Or if I want to compute averages, let's say, of this. But of course, I'm not drawing infinitely many samples. I'm drawing only one sort of sample collection, which means that I suffer a little bit from variance. The local minima issue is translated here in a mixing problem between modes. So if I have a distribution, a mode here, and I have a mode here, it's very difficult to design these samplers so that they actually cover both modes, especially because you often don't know where these modes are. If you know where they are, then you can deal with it. And it's hard to assess convergence, and it typically goes like you run multiple chains and you figure out, on particular intervals whether the Markov, the Monte Carlo estimates are very far off or whether they are convergent to each other. But it's cumbersome. So I'll say a few words about this Markov chain Monte Carlo procedure. So the simplest idea would be to say, well, this is complicated distribution. Let's take a simple distribution, G, and let's draw lots of samples from G, and then just throw away everything that's not, in this region in some more sophisticated way. It's rejection sampling or importance sampling if you just weight each one of these samples according to the probability of this thing. It's a nice idea, but it doesn't scale very well to high dimensions very quickly. This thing has extremely high variance in its estimates, and it's basically useless. So people have come up with other ways to do this. In high dimensions, particular Markov chain Monte Carlo is a really beautiful procedure to approximate these intervals. And the way to do it is to come up with a sort of Markov chain or a stochastic process that draws samples sort of sequentially, so they're hardly correlated with each other, and they start in an arbitrary position, but then they converge onto the correct distribution. So it's almost like a search process. It's like an optimization process, but then stochastically, right? And then sort of the first sample is drawn from a very different distribution, and the next sample is drawn from yet another distribution. Asymptotically, these samples will actually converge onto samples from the correct distribution. So then here is, in a little bit more detail, what that looks like. So you start with sort of initial. So I'm doing this now. So I'm sampling parameters theta, not z, but theta in this sense. But just think of this as any random variable that I'm trying to sample. I'm starting here, and I design this transition kernel here, which is under your control. So you have to design this transition kernel in a particular way that you can guarantee converges to the correct distribution. And typical things are detailed balance, which means that at equilibrium at the right distribution, the same amount between any 2 points, the same amount of probability mass should flow in one direction as it should flow in another direction. So this is the transition kernel. I will have a slide to explain one possible way to design this transition kernel, right? And then you sort of draw the next one, given the previous one, and this one, according to this transition kernel. Now, of course, there's good and there's bad transition kernels. A good transition kernel is one where the samples that you draw are very independent, or as independent as possible. Subsequent samples should be independent, and that looks like this. So as t progresses, basically these samples are sort of drawn independently, and if you can do something like that, then that's really powerful, because then every sample really counts as an independent sample. Where here, you see there's a lot of autocorrelation over these samples, right? The next sample really depends a lot on where the previous sample was. And that's really a not so desirable situation. And the reason is that, the variance of your estimator is going to depend on that autocorrelation, which I'll explain now. So first, the thing that we are interested in is averages over these samples. So let's say I have a function f, and I'm trying to compute an average of the function f over my target distribution as 0. Now I'm going to approximate that with a Monte Carlo sum, or Monte Carlo average, 1 over t number of samples times the sum over my function evaluated at these points, theta p, which come from my sampler. And by the way, I will have to ignore all that part, because that burn-in is from the wrong distribution. And again, figuring out which samples to ignore and which to keep is also non-trivial. Then there is a bias. You can compute the bias, which would be the expected difference between the estimate and the integral. The nice thing is, if you do this right, there is no bias. It's a bit over-exaggerated because, there is this burn-in thing. It's not quite done yet when you end sampling. So it's almost 0, let's say, in practice. And then there's the variance part of the error, similar to the first part when I talked about learning. The variance part, you look at the variance of the function f itself, divided by t, which is number of samples, right? But multiplied by this autocorrelation. So if there's a lot of autocorrelation, the variance is going to increase, right? And so this will give you much higher variance estimate than t. Now here's a particularly popular version of the transition kernel. It's definitely not the best. It's the simplest one, right? So let's say now we want to sample from this target distribution, which is proportional to the posterior distribution of theta given x. Now the way to do it is to come up with some proposal distribution, and you can think of, if I'm here in my space, right? I want to sort of have a region around me that I sort of sample this new parameter theta. So I just randomly pick from a Gaussian around myself, and that's my Q. And then I have to either accept or reject that sample. And I will accept with probability PA, which I compute here, and reject otherwise. So here you basically see detailed balance written out. So the denominator says this is the probability of being at my current point and moving from my current point to my proposed point. So that's the amount of probability mass that is moving from my current point to the proposed point. But this is the opposite, which is the probability of being at the proposed point and moving from that point back. And so we want these to balance out. So if this ratio is larger than 1, you always accept the point, according to this rule. If it's smaller than 1, then you accept only with probability given by this ratio. And you can then easily prove that this detailed balance property holds. So there's disadvantages. The burn-in is unnecessarily slow, typically, for these type of kernels, and the variance can always be quite high, also quite high. But I think the worst thing here is that this computation is order n, and so I have this saying that you can ask yourself, does your procedure pass the big data test? Okay, so what is a big data test? Imagine you have an infinite amount of data. So this is a learning procedure, right? You're trying to learn a parameter theta, or a posterior distribution of parameters. Now, if I have an infinite amount of data, that should be a really good place to be, right? And now I give you 1 hour to get the best model out of it, right? Now, one way to do it is to say, well, I just grab 100 data points and train a model. That would be a pretty good model. just ignore almost everything. But this procedure will not give you anything because it will get stuck at this point. Because here it has to compute, since this is a product over n points, it will take infinitely long to compute this ratio, and it will not do anything. Right? So this will actually not pass the sort of the big data testable. And we have spent some time in trying to improve on that situation. Say, well, that's ridiculous. Let's compute this thing on a mini batch of data, not the whole data. Now you're going to make a small mistake, so you're going to introduce some bias in your estimate, but at least you get a good estimate. So your variance is definite. Right? Okay, I'm not going to talk about that today, but there's a whole literature now on sort of stochastic gradient MCMC sampling, which is suitable for large data sets. Yeah, so...
Can you repeat the question?
Yeah, sorry. So the question is, what's the intuition for this thing? Why that's the right thing to do? So in the end, it's trying to prove detailed balance, which is really, it's not hard to prove, but intuition is that you want the amount of probability flow in one direction the same as in the other direction. That's detailed balance. And so here, there's two sort of reasons why these two factors make sense. This factor says, if my proposed point has higher probability than my current point, I'm moving up the probability sort of hill, and that should be good, especially when I'm burning in, right? And when you're burning in, you should always accept, going higher up. Once you're sampling, you might also want to sometimes actually accept things which are lower probability, because you sort of want to sample it to be. And this thing says, well, how easy is it to come back from the state I proposed to my current state? And this has to do with detailed balance, right? If it's impossible to come back, then in fact you can never get detailed balance, right? So you'll have to sort of look at that ratio as well. Well, if you are sampling from the correct sort of distribution, you should be able to go this way and that way. So you should be able to go back and forth in that space, right? Because otherwise you can never have detailed balance, right? You should be, if there's a zero probability of going back, then that will never satisfy detailed balance. There's more general sort of general procedures. Detailed balance is actually too specific. You can also have another sort of more general procedure, but I don't want to go into this now. So this is specific for balance discussion. So then the other sort of class of problems that are sort of discussed in much more detail is variational inference. And in variational inference, we basically say, well, I have some distribution P here, which is the green one, which is too complicated, and I'm going to choose a particular parametric family of distributions Q, and I'm going to try to make the best possible fit for Q so that it sort of looks like P. And one convenient choice is to minimize the KL divergence between the Q distribution and the P distribution. So that's not symmetric, so it's not really a distance, but at least, if this is, so if these are equal, it's zero, and it's only zero when these are equal. And as these, it's also, when, it's a measure of basically how similar they are. Now, you can rewrite this by throwing away some terms which don't matter for the actual fitting into this. And this is, again, the equation we saw in the beginning. So if we minimize this over Q, right, where this is log Px given that, I'm just assuming all the parameters are sitting here for now. It's just prior line, and this is an entropy term for Q. If I minimize this, I'm also minimizing sort of that KL. Right? So, and this is typically, if you have Q under control, you can either try to compute these expectations exactly, or you can sample from Q, and then to the learning sort of extract. And so now that we know how to do inference, it's really very easy to then look at how you can learn using the same principle. So for learning, we are interested in maximizing the log probability of the observed variables x given the parameters. Right? This is the object of interest. And as I explained, that is actually the integral of p of x given z times the prior of p of z. That's just the definition of what p of x for a latent variable model is. And now you can bound this thing by the following quantity, which is p of z, a tractable q z given x, depending on its own parameters phi, log of px given z pz, minus the log of qz given x, which is again the same equation as I had before, conveniently, right? But this is a bound on the log p of x. And so if we maximize this bound as much as we can, then over both the parameters theta and phi, then we also maximize this over theta, and by maximizing over phi, we'll get as close. The bound is as close to the evidence or the p of x and theta as possible. In fact, you can show that the bound has so the difference between the bound and the thing we are interested in is exactly given again by that KL difference. And this is exactly the thing we are minimizing when we optimize over Q. Our inference step is trying to minimize this object over Q. In fact, when Q is able to exactly model P, then at every iteration, this gap will be 0, right? And we will not make any approximation. And in fact, that's equivalent to the traditional expectation maximization algorithm. But when there is a gap, then it's called variational EM. And so that the two steps are now truly simple. We look at the bound, we maximize over phi, which is variational inference. In other words, we optimize Q. And in the M step, we maximize over theta, which is we learn our parameters. It's just coordinate descent on this P thing, right? And again, I said this is the most fundamental object. So here, so we see how it can be used for both inference and learning at the same time. Now there's a trick. In the old days, people actually didn't write Q of z given x. People just wrote Q of z. And then the procedure was, for every data point, you have a separate Q with a separate set of parameters. So every data point has its own set of parameters, alpha I, for that data point. And then for every data point, you would separately optimize this Q. Now the problem is that if you then get a new test point, right, before you can even make a prediction, you'll have to do an optimization for that new test point. So it's much better if you say, well, instead of having a separate Q for every data point, let's just have a function, very flexible function, going from x to z. So I stick in an x, and then I get a z out. Because x changes, my distribution changes, which is conditioned on x. But the parameters phi are now shared across all of the data points. And that's a really fundamental step, actually, because now for a new data point, I can just stick in the new data point, push it through my model, and get Q of z given x. And that's very fast. Right? So think of this as a neural net, for instance, that produces this distribution over z. And that's called amortized inference. It's being used for instance, variational autoencoders, which I'll talk about in a minute. Now, a little bit on the relationship between the distribution between graphical models and deep learning. From this perspective, if you look at this, right, this is just one conditional distribution. So let's say we have some conditional distribution, maybe going from input to labels. We're interested in this object P of y given x. Now, basically, I can write this as complicated as I want. So typically people use very simple things like discrete distributions or a Gaussian or something like that. But I can make it as complicated as I want. In fact, I can stick in a deep neural net. And in that way of viewing the world, a deep neural net is nothing else than a glorified conditional distribution. It's just a very complicated conditional distribution in a graphical model. And in fact, I was maybe, I don't know, 10 years ago, Sam Roweis told this interesting story that in machine learning, it's much better to invent an operator than to invent a new model. Because a new model only provides one paper, where an operator gives you a long range of string of papers. And so I propose to sort of invent the dphi operator. And the dphi operator basically looks for wherever you see a conditional distribution, and then take out the linear thing and stick in a neural net, and there's another paper for you. And in fact, especially for this talk, I looked for deep survival analysis. I don't think it exists yet. So Cox proportion hazard function, you can write it down like this. Here is your conditional distribution. Replace it with a deep neural net, and there you have another paper. So if you hurry, then you have your other paper. And here's another one. That's basically you look at, let's say, vector analysis, and you recognize there's a conditional distribution x given z. Now make that a deep neural net, and you have the variation autoencoder. Pretty simple. So here we go. Here's factor analysis, or latent variable model in general, prior of z and then x given z. Now dphi this one, conditional, and dphi this one, and you have the variation autoencoder. Doesn't look all that exciting this perspective, but you know. So there it is, dphi. You take a prior over z, and then sort of you write out all the sort of deterministic functions that are in this neural net explicitly. So here's the hidden units, which are deterministic, and they predict, let's say, the probabilities for the visible space. For instance, this could be the mean, the variance for a Gaussian, or it could be the probabilities for a multinomial distribution. Right? They predict the parameters that go into that distribution. You use those, and then you can sample x given z. Reversely, this is the dpified version of it's called the recognition model, and it goes through sort of a bunch of deterministic units, again, a neural net. It predicts a mean and a variance, because in the variation autoencoder, we basically always use Gaussians here. There's a few versions which use other things now, but let's say we do a Gaussian, and then we look at given x. There is a much longer history, which is that before there was the Helmholtz machine. It's from the 80s or something. And in fact, and we'll find this. Here's another interesting rule. If you want to be successful in machine learning, if you don't know what to do, go read old papers from Geoffrey Hinton, and then reintroduce them in sort of in a new shape. So this is a Helmholtz machine. Here's a Helmholtz machine, but there is actually a contribution, because they tried to train Helmholtz machines and they couldn't, and we now know and understand why they couldn't. So I'll talk about how to fix that problem. And later on in this talk, we'll have another paper from Geoffrey Hinton called soft, I forget what it was. Soft prior. We'll get there. But basically, it's some prior. I'll get there. It escapes me now. And again, you reintroduced for new soft weight sharing. That's what soft weight sharing. Okay, so now let's go into the reason why people came up with basically the WakeSleep algorithm. But the WakeSleep algorithm is a very strange algorithm where your update for Q and your update for P are actually optimizing different objectives. And of course, they wanted to just write down the variational bound, which was actually invented by Geoff Hinton and co-authors. And I'm sure they tried to optimize that thing, but it didn't work, right? And sort of, I guess then they moved to something else. But now we understand better why it doesn't work. So the first thing, so in the Helmholtz machine, you also have these neural nets that go from X to Z. So this amortized inference idea is actually already back from that paper. And again, I've written out the bound here. So, again, Z given X log, this is our model, X given Z, P of Z, and then here's the entropy term. And now, in order to learn Q, so learning P is actually easy. If I can sample from Q, then computing the gradients for theta is actually easy. The real tricky part is learning the Q. And so let's compute the gradient for the bound. When you sort of hit this thing, you can sort of, you get Q gradient log Q there. And it turns out you also, of course, have to go here, but then it turns out that gradient vanishes. You could write it out, and it actually is equal to 0. So this is really the gradient, and it's this term which is the nasty part. Because if you have, again, if we go to the big data setting, if we have a lot of data, we can't use all the data points at every gradient update, so we need to sample a mini batch. So that's our first sort of cause of stochasticity for this gradient. And the other one is that actually this Q is now actually from a pretty flexible family. It's no longer a Gaussian, with a linear map. It's actually a neural net. So it's a very complicated thing. And instead of sort of demanding that we can do sort of exact gradient sort of exact averages here, we're only going to demand that we can sample perfect samples from it. So we don't want to actually run a Markov chain to draw a sample from Q, because that's too time-consuming. We just want to very efficiently draw samples from Q. Now you can do that if you have this neural net going upward. And so that's another source of stochasticity, because now I have to sample from Z, and I also have a subsample from the data points. And so I have two sources of stochasticity, and if you try to compute this gradient, you basically fail. Well, you can compute the gradient, but if you try to learn, the variance is so large that you're all over the place and you can't learn. And this is one important lesson, I think, which is very often the problem with these models is in the actual variance of the gradients. If you can reduce the variance of the gradients, then something that before looked like you couldn't train, now actually you can train. So this is an important recent insight, that you should really focus on reducing the variance in these gradients. And then there's this trick, the reparameterization trick, and it's really simple. It's basically writing your Bayes net as a structural equation model, I think, isn't it? Basically, taking the noise outside and separate, and writing Z as a deterministic function of its parents and that noise variable. So now this conditional probability table is written as the deterministic function of the parents, the noise variable, and some parameters. And then epsilon, the noise variable, is drawn from some standard distribution. So it's important that that distribution is, let's say, a standard normal or some distribution. So now here is the gradient of this term that we always want to sort of handle, the bound. And now I'm going to reparameterize this Q. I'm going to turn that into basically P of epsilon by switching from Z to epsilon as the random variable of interest. So then, because it's constant and it doesn't depend on any parameters, I can just stick the gradient right through it, which is nice. So then it looks like this. So the gradient of log P theta, and of this term. But now Z here depends on phi, right? Because Z now depends on all of these things. So now so there's the Z here, which now depends on phi. So it means when you take the gradient, you take the gradient d log P dz, dz d phi, and here there's two actually. Take d log Q d phi and d log Q dz, dz d phi. Right? These are all the gradients that you take. Now, first of all, it's nice because you can take the gradient through, but secondly, what's really important is that there's a massive reduction of noise, and you can't quite see this right off the bat. It's kind of hard to see, well, why does that reduce my variance? So here's a very simple example. Let's say I want to compute the gradient of the expected, with respect to the mean mu, of the expected value of Z of a normal distribution with mean mu and standard deviation sigma. Now, a bit of calculation, you could say, well, that's mu, so the gradient should be 1. Right? That has to be. Now, if you do silly things, you say, well, I'm going to do it this way, well, the previous way. I'm going to do it. I'm going to write out this thing, right? And then you get this thing. So you get, you're going to write n log n times Z, and then you take the you compute the gradients, then you sample from your normal distribution, you stick them in, and then it turns out you'll get this expression, which you then evaluate over sample Z. And sure, on average, it has the correct value, but it has massive variance. Now, if you do it the other way, using reparameterization, you can very quickly see that you basically get 1 over S, sum of 1 over S, which is just 1, no variance at all, 0 variance. Right? So that's an example where you can clearly see that this reparameterization trick can reduce the variance in the estimate. And then here's an application, so you can sort of take these variational autoencoders and, use them for, let's say, semi-supervised learning. Right? So now I have 2 variables. I have a latent variable Z, and I have a label Y, and I'm just assuming that sometimes I've observed Y and sometimes I haven't observed Y. And then, PY, so I have independent priors on Y and Z, and they go through a neural net if X, P of X, P of Z. And then there's the reverse model, which is, again, one leg going to predict Y. So if Y is not observed, you have to predict it. So here's your P of Y given X. And then given Y or predicted Y and X, you then have distribution to predict Z given X and Y. So now you have to sort of write down the variational Bayesian objective. These are the standard terms that you get for sort of observed, non-observed labels. But there is one extra trick that you have to do, because in the end, you're actually interested in Y given X. So this is actually the discriminative deep learning algorithm that you're trying to learn. Right? So you want to upweight that path. And there's basically a fudge factor there that you sort of upweight that, the importance of that particular path. Because there's a lot, typically if this is a, an image, there's a lot of, bits that you can sort of explain here, and the error is dominated by all of these terms, where really you're interested in Y given X. So it's a little trick there too. Now here's a way, so Durkheim beautifully sort of developed this theory, and also, so here's a beautiful explanation, or sort of an illustration of how that works. So here we fly through Z space, and for every value of Z, we set Y equal to 0, 1, 2, 3, 4, 5, 6, 7, etc. And then we draw, so we draw from our generative model. So we have a Y and we have an X, a Z, and we go down and we generate the image X from our generative model. And then as we change sort of smoothly the Z variables, what you see is that all the Ys are sort of written in a different style. So the Z's now have taken up the role of modeling the writing style of the digits. Right? So it is, first of all, it's figured out that Y and Z should be, Y should be the label and Z should be other things. And moreover, Z is sort of the fundamental degrees of freedom in the data, and those are basically the slant and the thickness and basically the writing style. Okay, so stepping back a little bit, so we now have looked at basically this part of the graph, which is we've now looked at Bayesian sort of generative models, and they are really important in my opinion, which you can think of sort of as old school machine learning if you want, but it's a graphical model stuff. But it's basically what everybody else except for machine learning is doing. Right? So we like our black box stuff, but most of the rest of the world is just doing generative modeling. When they write down a model, they interpret the variables as meaning something, and then do inferences over these variables. And for instance, they write down a simulator, and the simulator is basically the physics, encapsulates the physics of the generative model, right? And I think wherever you go, you'll find these simulators very interesting. That's one way to sort of encode your prior knowledge or your expert knowledge into a model. But it's all in the generative direction. So Bayesian networks is a very simple generative model. There's a more general framework called probabilistic programming, which is also very interesting. I hope somebody will talk about this here too, which is basically now a coding language, sort of a software language, to program your own sort of generative model, including all the probability distributions. And you can hit a button, and then it will do sort of inference for you on the spot. And as I said, simulator models. Now, why are they important? Well, you can inject your expert knowledge, right? People know how the physics of a heart works, so you can encode that in this generative model. You can also model the causal relationships, right? So if you know A causes B to happen, causes C to happen, then you can actually put that into the generative models. Typically, the variables are very interpretable, and nowadays, there's laws that say if you apply, a machine learning model and that influences somebody's life, then you'll have to be able to explain how that algorithm made the recommendation or made the decision. So interpretability is going to become increasingly important. It's also very data efficient because you can inject all this prior knowledge, because you can do semi-supervised learning. It's a far more data efficient way to model. It's also robust to domain shifting, basically because of the work by Bernard here. If you think of modeling all these causal relationships, and if you actually capture the causal relationships, then then shifting the domain is not as problematic. For instance, I have this. Here's an interesting example. So in Holland recently, it came out that people who drive black cars actually pay a higher insurance fee. Now you can imagine that that's one way to predict whether somebody's getting into an accident. Unfortunately, that thing doesn't really generalize very well to maybe Japan, where males with high testosterone levels like to drive red cars, for instance. I don't know, but this is right. So the model shifts. If you shift the domain, but you have the causal relationship, then you're much close. So as I said, it facilitates like unsupervised and semi-supervised learning. On the other side of the spectrum, there's sort of deep learning, kernel methods, random forest, and boosting, which is this black box machine learning approach to things. This is very important too. For instance, because it's really a flexible map from input to target distributions, which we now can train very efficiently using GPUs. And it just is very successful, right? It just works very well. So this is something we cannot ignore at all. And it also solves the problem you're trying to use it for, right? You're trying to actually put something in and predict something, and it's much better to actually fit that particular map that you're interested in rather than fitting the inverse map and then inverting that using Bayes' rule in order to get what you want. Right? So again, there's a bias variance trade-off, I think, here. So here, you'll introduce bias here because you impose your own view of the world on your model. If you don't have a lot of data, that's a really useful thing to do. If you have lots of data, then it's almost certainly wrong. You're putting the world is more complicated than we can imagine. So this has high bias but low variance because it is very data efficient. This side, you have a lot of data, then and it's a highly flexible model, then you can get rid of a lot of the bias in your predictions. But because of flexibility of the model, you get a higher variance. And so another way to look at that is on this sort of data line. So all the sort of rage in deep learning is happening here, where we have lots of data, 10 to the 8, 10 to the 9 data points. And in Silicon Valley, they have this data, right? They have Internet of Things data, video image data, finance data, customer intelligence data. The data is available, so deep learning works very well for them. And they are in search of computational efficiency. Right? They're treating it mostly as an optimization problem at this point. And when you have all that data, that's probably the right thing to do. But on this side of the spectrum, when you're in health, due to privacy regulations, it's very hard to get your hands on data. Right? So in fact, you might get 100 or 1,000 data points due to privacy regulations. And now how do you fit a complicated model? In fact, in this domain, the number of observations is much larger than the number of data points, because this is the number of patients, which fortunately it's maximized at 6 billion, I guess. But here, the number of things you can measure about a person is extremely high. There's the genome, there's all the voxels of all of these scans. There's a huge amount of things to measure. So there is where we need statistical efficiency rather than computational efficiency. Okay, so here's the sort of autoencoder, variation autoencoder again, sort of written out. Where let's say we're trying to model you know, echocardiograms, we know disease label, we know hospital ID, we have some latent variables, we have some simulator model, we use our physics, we use our sort of causal relationships, we use expert knowledge in here. Then the reverse is basically giving the image and giving the hospital ID, try to predict all the latent variables from which you then predict the disease. Okay, so I'll very quickly go. So did you already have something on deep learning at all? No? So so I think one of the most successful deep learning technologies is really the convolutional neural net. And I want to emphasize that I think probably that for structured data, you know, a deep neural net is not going to give you a lot better results than a random forest or a gradient boosting machine or some of that application. So I think the main reason why this is taking off is because it's a very good way to signal processing. So signal processing looks at sort of very low level data like image pixels in an image, or you know, speech, sound is sort of the values of sound. Also, language is doing very well, so maybe that's a slight deviation from that theory. But it's especially these convolutional neural nets which are really starting to work really well under the sort of new computational power and the amount of data, the large amounts of data that we have. So how does that work? So you take your input image and you have a little patch here which you convolve over the image, and the patch is being learned, and I have a little sort of demo here. So let's say here's my input image, and here is a patch. Now this patch is learned. So if you do wavelet analysis, which is a very typical signal processing thing to do, and it's given to you, in convolutional neural nets you learn that object, right? Now you slide it over the image, so there it goes. I always enjoy that. And then you get your filtered image. So clearly this was a edge detector. So you'll find that sort of here all the edges it really likes, the positive and the negative side to the edge, the signed edge. But everywhere there's no edge, like here, the filtered image is 0. Gray is 0. Then there's the next step typically, which is pooling, which is for every 4 pixels, let's say, you pick the most active one. That's the one. Pretty simple. And there's 2 reasons to do this. I think the first reason is that it saves a lot of memory, because you're going to have a lot of these filter maps, especially during learning, that you have to keep in memory. It saves memory by making them smaller. The other sort of side benefit is that it will actually implement small invariances. So if I wiggle something small in the input, you could imagine that in a region where you get 4, filter values, maybe the maximum shifts from one, pixel to this neighboring pixel. But since I was picking the maximum active pixel anyway, it doesn't change anything here. So in other words, I can change things here that don't reflect here, which means that I'm starting to build in an invariance, and this is typically a good thing. And then I have to put the whole thing through nonlinearities, and I have to repeat this many times. So let's go back to here. So so here's one of those patches. These filter maps you shift, you convolve them, you get one filter map. You have many of these, so you get many of these filter maps. Then you pull things down to a smaller size, and then you repeat. So you get a new patch, you apply it now to all of these, which will give you this here. And I have my next filter patch, it will give this set, next filter, this set. So you see the number of these filter maps is exploding. But fortunately, they also get smaller, so the number of pixels they have to keep in memory is sort of about constant. Okay? So then the procedure is really a forward map, which goes filter, subsample, nonlinearity, I guess, filter, subsample, etc. And then, of course, we have to start learning, the values of these patches. And the way to do that is really surprisingly simple. You write down an error, an objective at the end, an error, and then you just take the derivative of that error with respect to this pixel, that pixel and that patch. Right? It's really that simple. In fact, it's just applying the chain rule. You have to backpropagate through all of these layers to get the derivative of that patch. You have to do some bookkeeping to make sure you don't redo computations that you can store. But these days, it's like doing a matrix inverse or computing, a square root or something like this. You don't bother about actually figuring out what the algorithm is that does it, because it's all in software, and it's called auto differentiation. So pretty soon, probably people will forget how derivatives and just push the derivative button on their software, and then thing will work out. Okay, and then there's many tricks to the trade, and because I want to sort of make progress, I'll just say one that I need later is dropout, but there's many other ones like resnets, and there's batch norm, and whatever else you have. I'm just going to do dropout here for a minute. It's a really simple idea which says, for every data point, just randomly kill half of your neurons. And what I'm going to argue is that this was, again, sort of a smart idea by Jeff Hinton and his collaborators. And what I'm going to argue is that there is actually a Bayesian interpretation, very nice Bayesian interpretation of what that is. But sort of on an intuitive level, this guy should not rely on these guys to be there in order to do its computations, because if it relies it can sort of really collaborate and start to overfit. If it can't rely on these other ones, it sort of has to do some somewhat independent calculations, or more independent. Okay, so let me quickly go through a few examples. This I'm going to do very quick. So only in 2017, there were 3 fantastic results from these convolutional neural nets. The first one is here by the Stanford team, where they took a neural net, they fine-tuned it a bit, they had 130,000 images of skin lesions, they had to predict into about 757 different classes, and then the most important contribution of this paper was that they compared it to 25 dermatologists. And I think these people knew very well they were competing within the computer, so they were on the edge. They were trying hard to do very well, I think. And I've had them, these are maybe Stanford dermatologists, so they're pretty good, sure. And then, so this is the curve that the computer at all operating points produced for specificity, for sensitivity. These are the dermatologists. And the most important thing to know, if you're below the curve, you're not doing as well as the algorithm. And I think there's one person here that's doing well. But certainly the average is below. And I think a dermatologist, that's right before dinner, 5 o'clock for lunch, somewhere, some province, might just do quite a bit worse than this. So my point is, we are at the point where these kinds of very constrained tasks can be done very well by computers. And here's another one from the Dutch news. It says computer can predict cancer better than the pathologist. This is breast cancer. And here is what's called a histology slide, which is a huge slide with a gigabyte of sort of pixels. This is blow up, which is, you see all the cells in there. You need to predict where the tumors are. And again, they compared it against humans. Computer did 89% correct, pathologist 73% correct. Here's another one, retinopathy. If you look in the inside of your eye, then at the retina, you can look for lesions that are then predictive of diabetes. And again, you can compare humans, machines, and in this case, they're pretty much on par. What's so special about these 3 problems? Well, first of all, they're all in 2017. But the second is they all use the same network. So this network is called Inception V3, and it's trained on your vacation pictures and family pictures. And it was, a bit, mutilated. So I think that the predictors were taken off and retrained. There may be a little bit of fine-tuning on that, and you get absolute state-of-the-art. Right? And this is a bit of the magic of deep learning, because why is it that we can train a model in one domain that's completely different, and then move that to another domain, and work so well. So I think there's one of the mysteries that we still have to sort of figure out. Okay, so I've argued that these conv nets work really well, but there's also a few things that are not very good about them. This is just one. There's a few other ones that people don't like about them as well, for instance, adversarial samples, but I think they're way too big, and I'll show they're way too big. they consume way too much energy, and they also use too much memory. So we need to make these, so I think at some point the game will be how can you efficiently make them smaller so that they can run on your, still run on your cell phone, right? Because if you have, make them smaller, you can use more of them or bigger ones that are more predictive. So in particular for your cell phone, it's important, you know, there's a certain amount of heat that needs to be dissipated out of your phone. Whatever you do, you can't get rid of it. If it's in your pocket, you know, you don't want it to burn through your trousers. You really want to manage the energy spending. And so we looked for a Bayesian deep learning, although I have to say the causality may be the other way around. We did Bayesian deep learning and we applied it to depression, but anyway, I think that happens a lot in our field. So, so Bayesian deep learning is a very nice tool to do model selection, and in this case we can try to apply it to pruning. It can do automatic regularization, and it can also produce uncertainty. And I think this uncertainty part is also not to be underestimated, because anytime you actually want to use, let's say, a prediction of a model in the real world, right? You want to act on it, or you want to build sort of reinforcement, an algorithm around it that sort of changes things in the world, then you really need the uncertainty. For instance, if you think about a doctor, and the doctor gets sort of an algorithm that predicts, this person has disease X, right? If the probability of X is like 99.9%, then you might just go ahead and start treatment. But if it's 51%, then the right response might be to do additional tests, right? And also for cars, if cars get into a new situation, if they might have, many times they might make the correct decision, but if you don't have the uncertainty, once in a while they might very confidently make the wrong decision. And in that case, it's much better to say, hey, I don't know, you grab the steering. So this is a sort of cartoon picture of what Bayesian deep learning is supposed to do. So this is the non-Bayesian version, where you basically only model the noise level in the data. And a Bayesian model should sort of be aware that away from the data, the model should be more uncertain. And I'm sure you get a lot of Bayesian, because I hear Zupin is going to talk about Bayesian learning. So this is just, I guess, too much, but let's be introduced anyways. So the core object in Bayesian deep learning is this posterior distribution. So M is the model, X is the data, theta is the parameters. So the thing we really want to compute is the posterior distribution over the parameters given the data and the model. And that's quite easy to write down. So it's X given theta, and give theta divided by P of X, all conditioned on the model. So that's just Bayes' rule. But of course, it's not so easy as that, because this thing is hard to compute. And in fact, you cannot do any integrals over this object typically. And this object P of X is the evidence, which is then the integral here over the parameters. So that's how good this model is in modeling that data. Then predictions are important. So now I have a new data point. I want to compute the probability of X given all the data. So the probability of a new X given the data and the model. Now here you need to integrate over your posterior. Here's the posterior, you need to stick it in here. So basically, look at the likelihoods and weigh every likelihood with the posterior distribution. Is how likely is that parameter? Then you can integrate over all the models to get you the evidence of the data. And you can do model selection by looking at the posterior distribution over the models given the data. And there's this interesting phenomenon that also in Bayesian learning you pay a price if you entertain a model that's too complicated. And that's given in this picture. So if you have a really complicated model, that's the green line. So here you imagine there's all possible data sets that you could have generated for this particular problem. Now, if you have a really complex model, it tends to put a lot of probability distribution over all these data sets, because it can model all these data sets. It's very complex, right? So it's going to actually model a lot of these data sets. The problem is, though, that it's a normalized distribution. So for any particular data set, it doesn't have a very high probability of X. So P of X given M, is basically here. That's not super high. So you can think of this as, again, a high variance. And here there's a model which is a much simpler model. Now it puts all its probability mass on a much smaller set of data points. You could imagine sampling basically data sets, right? You could imagine picking a data from the prior, and then picking a data set, get data, and just looking at all the data sets that you have, right? And then if you have a very complicated model, picking from the prior and having sampling, you'll get all of these data sets here. For a simpler model, you get very much smaller set of data sets. So it's peaked at some data set, but maybe that's not the one that you actually observed, right? And so there's some intermediate complexity, basically, that's optimal. Now, if you would know exactly how the world works, how nature works, then this clearly is the best model, because then you can shift it, right on top of X. So that's great. But typically, you have biases in the way you model the world. So then the best thing to do is to give a little bit more flexibility, but not too much, because you're sort of overfitting. It's not called overfitting in Bayesian learning, but it's like high variance. Okay, and then there is again. So now, again, our sort of friend equation. But now I've switched z for theta. So now we are learning parameters rather than hidden variables, right? The difference between a hidden variable and a parameter is there's one hidden variable for every data point, but there's only one parameter for an entire data set, right? So that's different. But we can still write down the same equation, the bound, but now we have a variational distribution over the parameters theta. So now here's a very nice connection to compression. And again, this goes back to papers by Jeff Hinton, where you look at this first term, which is the expected value over the p given, averaged over this Q distribution, and you can think of that as the error in the predictions you're making with your model P. So maybe to explain. If I want to send my data to you, then one thing I can do is I can first locally train a model, and then I first send you the parameters of the model, which cost me something, and then I ask you to make predictions with that model, and then I'll just send, because I can do the same thing, and then I can send you the errors, right? And because the errors are usually small, they can be encoded much more efficiently. And then this is a term which basically tells you how expensive is it to send you the model. And this is the term that tells you how expensive is it to send you the corrections for the errors. So now what we can do is we can you use a very simple idea which is called soft weight sharing, which basically says, well, let's train a mixture of Gaussians model on the weights as a prior. So we take the prior as a mixture of Gaussians model on the weights, and we train that at the same time as we train the weights for making predictions. And what will that do? I'll show you in a minute. So first of all, here, this is the prior over the weights. It's a mixture of Gaussians with a very large peak at 0. We want sparsity. We want most of these weights to go to 0. And we want to cluster the rest of the weights. Basically mean we want maybe 16 or 8 or 16 different values for the weights, not more, right? So every weight in the neural net gets mapped to 1 out of 16 different real values. Now I only have to store 16 real values, and I have to store a pointer that says this weight, is equal to this cluster, this weight goes to this cluster, etc. So that's a compression right there, right? And if you train these jointly, what will happen is that for the weights are, so usually when you train a mixture model, the data are fixed and it's easy, you can just cluster the data. But now as you're training your mixture model, the weights are moving, so it's like a moving target, right? But as it's, it can win a lot by making these clusters very tight, because to make them very tight, and then there's this complexity term. And here is basically the end of learning. You'll see that it has learned basically a number of clusters, and it put all the weights basically in these clusters. Here's a little demo where you can see how that works. I have 5 more minutes, or yeah, your chair. It's 5 minutes. Okay, so you see here, this is the weight distribution before, and this is the weight distribution after learning. So that if you can see that it's starting to cluster these weights at particular values. First it sets, there's a big spike at 0. Then you can look at the results, and then something surprising happens, which is that, so So let's say for this model, this is a pre-trained model. Now you're going to try to sort of press it. So 0 means this is accuracy here, and this is compression rate here. And then sort of 0 means that here actually you're doing better than the original model, and here you're doing a little bit worse than the original model. But you can see that without any loss in accuracy, you can compress about 60 times, which means for every 60 weights, you just keep one around. The rest you throw away. Right? And surprisingly, you can do 20 times compression and actually become more accurate. Right? So it just looks like a paradox, but the thing is, of course, that this clustering effect is actually also a way to regularize. And then in the remaining few minutes, I'll just say a few words about how you can take this one step further. And the core idea is here that if you think of a neural net, then here's all these weights hanging around. And in a Bayesian setting, you have stochasticity in these weights because these are random variables. But if you look at it, all of this stochasticity has to go through these hidden units anyway. And there is a trick, which is that you can marginalize out all of this stochasticity in the weights and replace it with stochastic hidden units. And that's equivalent. It's a very interesting observation. It is an equivalent formulation of a neural net where it's a deterministic neural net, but then you add noise on these hidden units. And that should sound a bit familiar because dropout is exactly adding noise to these hidden units. In fact, its dropout noise is one way to add noise, but you can also do things that look a lot like a multiplicative Gaussian noise, which approximates very well. Right, so the plan that I'm not going to do, but I'm just going to sort of lay out here is to marginalize out the weights for the price of introducing stochastic hidden units, reinterpret the stochasticity on the hidden unit as dropout noise, and then use sparsity in various ways, sparsity-inducing priors to prune out weights and hidden units. Right, so that's a program that we followed, but I have to sort of hurry up now. There is an additional trick that you have to do, which is called local reparameterization, to again reduce the variance. So the same theme coming back here. If normal reparameterization is not enough, you have to do another thing to reduce the gradient variance further. This is called local reparameterization. I have to sort of skip it, but we can look at the conclusion so that we can use this trick, this local reparameterization, to further reduce the variance. Then we can write down a bound like this, where F is the sort of activation of the last unit. So we get distributions over F given B, which is the activations of these units, and then B given X. So we get sort of these variational distributions now. Have to hurry on. We then reinterpret stochasticity as dropout. Then we can put sparse priors on the weight. So this is a super sparse prior on the weight, and we can compute these terms in the bound now exactly, and we can train the dropout rate. So here's the trick. So you can now learn the dropout rate, and if the dropout rate goes to infinity, basically you should prune that weight because it's always off, right? And then here's maybe a nice demo by these guys here from Russia. They implemented this, and here you can see as the algorithm runs, the accuracy goes up or stays the same, and the compression rate goes up, right? So here's 260 maybe that it reaches. And here you can see these are all the filters, and then basically most of the activations in the filters are 0 now. Here's it for the fully connected layer, right? Almost nothing left. But that's pretty bizarre if you think about it, right? So why did we need this very large neural net in the first place? Probably for optimization reasons. But the fact that you can prune out everything in hindsight is saying something about neural nets. Okay, so then the last thing, don't look at the equations, look at the conclusion. So now we're going to use hierarchical priors, which you put a scale prior on the unit, and then you have a different conditional distribution for the weight given that prior on the unit, but then sort of the prior for weight out for all the outgoing weights given that unit. and then you do some trickery, and then you can now actually start to prune the individual units. Now, it's very important that removing weights is actually not very useful for compression. It's very hard to encode that. But if you remove an entire unit, then you just have a smaller model, and that's very easy to use in compression. So using that, we can get up to 400 times compression rates here. So that means 1 out of 400 for a particular model, right? So this is the net 5, pre-trained. Press it at 1 out of 400 weight keep around. The other nice thing about the Bayesian perspective is that you have a posterior distribution, so you know how your weights are fluctuating, right? And you can just write out every weight in bits, and you can just say, well, which bits are fluctuating heavily under sampling from the posterior, and those that are fluctuating sort of wildly, just remove them because they don't carry information. Just keep the significant bits which remain stable under posterior sampling. And so then at the same time, you can actually you can compute the fixed point precision with which you should keep that weight in. So there's another sort of what I call a Bayesian bonus by having access to this posterior distribution. Okay, so I'm out of time, so here's the conclusions. So deep learning is not a silver bullet. It is mainly very good, and then I really mean very good, at signal processing. But don't generalize this to every other problem, right? Structured data is not necessarily better than a great machine. Optimization is playing a very crucial role in deep learning. And in our case, for instance, reducing the variance of the gradients was really important to get the models to run. But I would also emphasize that at least when you're not working with huge data sets, then at some point statistical considerations are also important. I think it's kind of interesting to try to merge deep learning with more classical graphical model approaches and sort of this idea of deep learning as a glorified conditional distribution. Now, for the Bayesian deep learning, it has it can model output uncertainty, and it has a very nice interpretation as modeling dropout. As a principal interpretation as dropout. It also helps with adversarial samples, which is also considered a big problem usually, which is you just change your input a little bit. You can't even see it, but it now puts the image in a completely different class, and actually very confidently as well. Now, this helps quite a bit with reducing that problem as well. So the Bayesian approach is actually a nice way to solve some of the problems. But I should also emphasize there's a lot of things we don't know about Bayesian learning, and I think we should maybe make a list of it. There's this interesting paper by Semi Benjo's group in DeepMind where they look at sort of generalization performance of these deep neural nets. And it turns out that if you just randomly permute the labels, you can very easily actually get zero training error if you push a bit on the optimization. Yet if you don't permute the labels, there seems to be a phase where it comes up with a solution that actually generalizes very well before it sort of starts to overfit. Why is that? The strange behavior in the face of adversarial samples clearly is a concern and also an interesting challenge for us to solve where they're coming from. And then this over-parameterization by up to a factor of 400 sometimes is also telling us something about, something we don't understand about neural networks. I'll leave it at that.
Okay, so that's good. So back to the compression thing. So does that method sort of compress and sort of most of the weights are dropped? Has it been tried out for transfer bus? So for example, when you use like the inception net and cut off a couple of layers, so if you use this one that's been compressed and then cut off as the next something else, performance drop. I assume it would because it's probably evaluated the same task.
So you're saying you take inception and then you compress it.
Yeah, and then
you first compress it, or you compress it for a particular task?
First compress it.
Okay, and then see how well it still transfers.
Yeah.
So you're asking maybe the over parameterization is helping for transfer learning.
Yeah, either that, and I'm assuming since is it compressed for a specific task or just general?
It's definitely compressed for a particular task.
Okay, so is it possible that it's abusing sort of, because I've seen that the metric used was accuracy. Is it possible that it's abusing the threshold decision bound? So in case like where you have a like an
But it is a general, it is a test error though, right? It's not the training error.
yeah, but still it might sort of find like, okay, so I don't need to be so confident for some cases if I just get them right.
Yeah.
So unless instead of like 90% confidence you get like 55, but it's good enough for the decision. Has anybody like violated that stuff?
I think it's a very fascinating idea. So we did look at what happens after compression to adversarial samples, and the jury is still out a bit, but I think it becomes more sensitive to adversarial samples. But we haven't looked at transfer learning at all, so it's very hard for me to give an answer to your question, but it's a fascinating thought. Right?
Thanks.
So she thought because of the it was about a lot of the notes, and why is it that adding or adding?
Yeah, more weights improve the performance. So there's a lot of difference between sort of. Oh, so you're saying you have a Lunette 5, and instead of pruning, you're going to make it bigger, and then you hope that performance goes up.
Yeah, I mean, it isn't that off like up too big or something.
Yes. So I guess you add more, and then you sort of regularize a bit more as well, or something like that. I don't think it's necessarily contradictory to this, because then I could take that model and start pruning and trying to keep that level of performance the same. Right? So there's something in the optimization. If you give it a lot of space, right, and a lot of room to optimize using all of these parameters, then it can find better solutions. So that feels like it's an optimization problem. Then once you're at that solution, you can then start pruning things away again and keep the accuracy. But I think I could imagine having a system where you take a net, suppress, or not, or add more layers, suppress, add, suppress. Just that every time you compress, you keep the performance the same. So I think it's not contradictory, that observation that you're making. It's probably right, which is you need lots of parameters to do the optimization, right?
So I was wondering, do you think that like we have stateful parameterization that opens the door for new evolutionary either evolve connected or directly evolve states?
I don't necessarily know why that would be very helpful for that particular optimization algorithm, although I might miss something. I'm not an expert in it.
So it's not what I mentioned. So optimization is basically search. So kind of have much lower than basically.
You mean like you want to compress you first compress and then you do evolutionary computing, or?
So basically, I would evolve a representation that's sparse by simply restricting pairs. So I have 40 the rest of the dimension representation. Then I evolve those.
So you build in the constraint that you want, a sparse representation in the evolution. Now, so it turns out that it would have to invoke some magic on the neural, or what do you call it, the evolutionary computation, because if you try to train a neural network with the same number of parameters as we get after compression, you cannot nearly get as good performance. So you have to first optimize in the big space and then compress. You cannot do the opposite, which is start with a constraint and how much parameters you can have and then start optimizing. So
still optimize also with don't have to question.
No, I agree, but what I don't see is why that method would be able to circumvent this issue that it's much harder to optimize in a much more constrained space. So that's why I said I think that there would have to be some magic that I don't understand about that evolutionary method that would be able to optimize under all of those constraints. But it's something you should try, I think. You know, I could be completely wrong, I should say.
Hi, thanks. So somewhat more elementary question about the function. So if I have a very big neural network, I want to teach it, and I've trained it on a data, do I just have to give the network with parameters that I learn? Do I have to also give the data, or just the architecture and just the data?
No, we do need the data as well because we keep training basically using sort of this Bayesian method. You can also train. You can actually also go from scratch, right? You don't have to compress an existing model. You can just start, you know, with a very big space, and then you slowly let the sort of sparsity priors take care of the pruning. And we've done that too, and that works well as well. But we don't do it without the data. So one of the nice things about this is that you keep training basically, and that as you are training, you sort of remove the bits and pieces of the model.
I wanted to know if I didn't understand the whole with how you specified actually. I mean, in details the algorithm. But did you try something, for example, just starting with the net that is trained or you train, and then adding gradually more and more bigger constraint on L1 constraint on the weights, so that sort of it would push the weights to go to zero if they are not necessary.
Right. So I think that's not going to work for the reason that an L1 constraint actually also hits the big weights. So the thing is that if you put an L1 constraint, it likes to make small weights go all the way to zero, but it also pulls big weights in to become smaller, and that's not sparse enough, right? What you really want is, you know, small weights they get to zero if they're not useful, but you do not touch the big weights because those are the ones that are actually doing now. You know, those are just the scaffolding that's doing all the modeling for you. So I think we might actually have tried something like that, but I think the performance will actually degrade.
Yeah, to continue on that question, also set up a L1 some Cauchy like prior of trade-off between six.
That's right. So we actually our priors are, you know, very much Cauchy-like. Actually, we use horseshoe priors, which are nice, which are great. Then there's still the additional issue that you want to, you know, put sparsity on the nodes and not on the weights. Because for chip design, they want to actually remove nodes, not weights. So that, you know, then you need slightly more sophisticated to having a hierarchical prior.
So just following the lady's question there, we had a lot of lectures from Shai in the last couple of days. I wonder if a question regarding adding layers and pruning contradictory or not. Would it be fair, for fair intuition to say that adding layers is kind of like allowing a richer function class for search? A pruning is in that bigger function class, and then you can make function simpler, so which is not contradictory. So you search for a bigger class, which there might be simpler functions that you haven't considered with fewer layers, but then you prune to just search for simple functions.
But if you could characterize the simple functions directly, search in that space, would that be better then? Because your actual function is in this smaller space, and then you would want to search in that space. And I think there's, you know, it's an interesting thought, but I wonder whether if you make this space too small, the optimization is going to be very hard. So I strongly feel there is not like finding the right function space is not the only consideration. There's a strong element of optimization which gets easier if you make the model big. But
Like the mathematical trick.
no, it's just, well, as a mathematics, it's like the surface. It's like if you're in a high, you want to find a minimum, and you allow yourself many degrees of freedom. You know, there's always different routes to get there, right? There's just more ways to get to the solution if you have searching in a big space. If you're constraining yourself, you might get into, you know, local minima, which might turn out to be saddle points if you give yourself a lot of space. It's something like that, but clearly we don't know exactly what it is.
So in the variational EM algorithm that you introduced just now, one has to make a simplification assumption on the Q distribution. And when you try to estimate the model parameters at the same time, right, does that not bias the estimation of the parameters away from the maximum likelihood estimate that you would have gotten in the standard EM algorithm? And is that necessarily a bad thing? And if it's so, is there any trick to get around that?
Okay, these are many difficult questions. So I think the first answer, the answer to the first question is yes, you will introduce a bias by introducing a Q. And in fact, a typical thing to do is you factorize the distribution of the latent variables and the parameters. That factorization is clearly ridiculous because if I wiggle my parameters, my latent variables are wiggling with it, so there's correlations that you ignore. I think it's problematic to do this to some degree. If you could avoid it, I would prefer not to have it. But I also think recently people have become more and more sophisticated about building very flexible Q distributions, right? Because we moved from the requirement that you have to be able to compute an average exactly over that Q to I only have to sample from it efficiently. And now there's normalizing flows, and there's all sorts of tricks to make these distributions actually very, very flexible and approach the true posterior very closely. So I think that's the thing I would. And then actually, it's also interesting that you are starting to sort of the MCMC world and the variational world is starting to get closer, right? Because we're now sampling from these Q distributions. And on the other hand, the MCMC distributions we make more efficient by something I haven't talked about, but making not depend on only to depend on mini batches. These things are getting closer and closer. So basically, you're trying to get away the bias, so unbiased estimators, and sort of manage the variance.
So I was wondering if you try to combine hash methods both with model distillation. So for example, train large network, then use this large network and a smaller network. I think our results show that smaller networks get better results with that. Wondering when you train the small network like this, and then try to compress it, you end up a larger network. So
yeah, that's a very fascinating thought. So we had the thought of actually trying to combine distillation with compression, but we certainly didn't do it. And it would be a really cool project to actually try out, right? So you know, distillation is also a way of compressing that, where you don't use the data, but you basically also use a lot of other points in your input space, not necessarily the data, and you generate lots of sort of fake labeled examples because they're predictions from the complicated model. And though that kind of procedure could also help you compress even more efficiently. So that's a really interesting direction too. I haven't tried it.
It's like more conceptual, and it's on the question like related to the yesterday lecture from Sure. So the question is, yesterday I mean, we've seen about the VC dimension and how it relates to the number of parameters in different networks. And I was wondering, like, whether like the phenomena that this networks doesn't, the network doesn't overfit is because those parameters, even though they are quite large, but they are not used. So you can compress what means that are not. So even though you have a lot of parameters, you don't overfit. Do you think there is a relation to that?
Yeah, I think that's very likely. The only so clearly it's not using a lot of the capacity that it has, because you can prune without being penalized for it. But what's kind of fascinating is that when it's optimizing, why is it first going through a phase where it finds a model that generalizes well before it starts to sort of overfit? And you know, there's something in this dynamics of this learning that we really don't understand.
Did you try like compressing for if it looks like before overfitting and after?
I guess we took a model that was given to us and which was properly regularized. It's a good model, and then we started to compress. Typically, when you compress, you're not starting to overfit. There's a danger of underfitting, I guess.
Yeah, I mean, like when you compress, you start with a well-trained that model stops like early stage for fitting course. I was wondering if you take a model that overfits, what will happen if you try to compress it?
I would think that actually, in my slides there was a little bit of that. That if you start to compress and you don't compress too much, there is a regime where you can compress by maybe 40 times. It's already you keep 1 out of 40 plates, but you improve the performance. Right? So there is always this phase where sort of the compression is actually a regularization effect as well.
Thanks, Max, for this very interesting talk. Pity that you couldn't be here for longer. We also have a bag with some goodies. So yeah, it was great to have you here. So Max is around until tomorrow.
Yes,
probably also here tonight at the poster session. So yeah.
But thanks for all the great questions.
That's great. Thank you.